Okay, before looking at data abstraction and object-oriented programming, let's take a look and see what explicit state is good for. So let's introduce a definition. We say a program is modular with respect to a given part if we can change that part or update it without changing the rest of the program. So by part, we mean many possible things. It could be function, procedure, component, an object, a module, etc., etc. And we show by means of an example that using explicit state allows us to make a program modular, which is not possible in the functional paradigm. So here's a scenario. Once upon a time, there were three developers, P, U1, and U2. P has developed a module, M, that implements two functions, f and g. So here on the right is the module definition. So f is the module definition, and if you want to create the module, you call this, it's a function, and you instantiate the module m. And u1 and u2 are both happy users of module m, and so it goes until one day u2 writes an application that runs slowly because it does too much computation. So u2 would like to understand why this is the case. So u2 would like to extend m to count the number of times that the function f is called. Okay, so we have here the function f. We want to count how many times it's called. u2 asks p to make this extension, but in order to save everybody a lot of work, the extension should be modular so that no programs have to be changed to use it. Okay? Oops! This is impossible in the functional paradigm because f has no memory. F does not remember what happened in previous calls. It cannot count how many times it was called, and m neither. The only solution is to change the interface by adding two arguments, fin and fout. Fin is the incoming count of how many times f was called, and fout is the outgoing count. So fout is fin plus 1. And we have to make sure that the fout of each call to f is passed as fin to the next call. Okay? Then it's fine. But this means that m's interface has changed. And all the users of m, even poor little u1 who did not ask for any change, have to change their programs. So u2 is unhappy, but u1 is especially unhappy since it makes a lot of extra work for nothing. So what's the solution? Well, cells to the rescue. The solution uses a cell. So what we do is we create a cell when we instantiate the module, and we increment the cell inside f. So here x is created, and here x is incremented inside of f. And because of static scope, the cell x is hidden from the rest of the program. It's only visible inside the module. Okay? And we extend m's interface by adding a new function, m.c, but the existing functions m.f and m.g are not changed. That means people that already use m can keep calling it in the same way, and the new function m.c can safely be ignored. So p, u1, and u2 live happily ever after. So the moral of the story is that there is some very good use for explicit state. Okay, let's make now a comparison between the functional paradigm and the imperative paradigm, a plus and a minus. So the functional paradigm, a component or function, let's say, never changes its behavior. So if it's correct, it stays correct. That's a plus. But the minus is we can't change it. We can't update it. So the plus is also a minus. If you want to update it, often you'll have to change the interface, and many other components must be updated. Okay, now the imperative paradigm. The plus is you can update the component without changing the interface by using explicit state. So the system is modular. But the minus is a component can change its behavior because of past calls, and it might break, for example. Now, the trick is sometimes it's possible to combine both advantages. If you use the state in a disciplined way, so you can use the explicit state to manage the updates, but you make sure that the behavior of the components does not change. And that's a good use of state, and then you get the best of both worlds.